All right, so onward and upward. Now that we have a sense of how we can find probabilities, let's take a look back at some of that rounding potential issues that we might have. So when expressing the value of probability, either give the exact fraction, the exact decimal, or round off final decimal results to 3 significant digits. So significant. Now it doesn't just say 3 decimal places. And that's because, again, you might have some decimals that are really, really small. And so if you rounded them off, it would look like it's 0. So that's why they use the term 3 significant digits. So let me just explain that. And we shouldn't have to worry about it too often, but just in case you see it, you'll know how to do it. So when given final answers, they either use a fraction, so 1/3, 2/8, 5/9, etc., or give as decimals. So significant digits are generally non-zero digits. And also don't forget to round appropriately. So something like 1/3, which is not very small, we can round it off to 3 decimal places and it's not a big deal. Same idea with something that terminates, a terminating decimal. So 0.25, not 0.250. In this case, I probably wouldn't get too picky about that if you put the 0 at the end or not. And again, something like this, you would run around that 3rd decimal place up. But what happens when the decimals are small? So however, with a decimal with zeros after the decimal point, start counting significant digits only after you reach a non-zero digit. So for this one here, we got a lot of zeros after the decimal point, but as soon as we reach the 7, that's considered the first significant digit. So we got 1, you got the 6 would be the second one, and then the 8 would be the third one. So that's where we would want to round to, not 3 decimal places, because again, if we rounded it to 3 places, it would just be 0. So it's not really giving us anything. But 3 significant digits would put us on the 8. So if we round it to the 8, the 4 says we would leave that 8 alone. So this is what that rounded to 3 significant digits would look like. Now again, we're only talking cases when the numbers are really, really small. If there's something standard like this, you're not going to even worry about it. It's going to be 3 decimal places. So, but just something to keep in mind depending on how it's phrased in the textbook or how it's phrased on the online homework. So be careful of that. So let's just do one just to make sure we got it down and see what we get. So let's round this to 3 significant digits. So we have 5 out of 123. So let's see what that equals first. 5 divided by 123 equals, so 0.04065. Okay, so let me write some of that down. So 0.0406507, and it keeps going. Okay, so now we have our decimal. So what digit are we going to be rounding? What's the 3rd significant digit in this decimal? So would this 0 be significant? So the first significant digit is the 4. So the 4, this 0 is considered significant once you've hit another significant one. So even though this 0 was not, this 0 is. So first one, second one, and then the third one. So now if we're rounding to the 6, what do we do with the 6? Do we leave it or do we round it up? Hopefully you're saying round up, round up, round up. So this should be 0.0407. All right. Now, like I said, you shouldn't have to worry about that too often, but in those cases when they're really small decimals, 3 significant digits is the proper terminology. Okay, so that's one thing we got off the table. Let's take a look at this next part, which is talking about percentages. So percentages are sometimes used as probabilities and vice versa. However, we're going to make it clear that we only want to use percentages when requested. Otherwise, write probabilities as fractions or decimals, and I would even cross out the fractions and just say decimals. So only write them as percentages when requested. If it doesn't say anything about percentages, then don't do it. Write it as a decimal. Okay? Now, a comment on sample sizes and probability. The law of large numbers. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. What on earth is that talking about? Okay, let's look at an example. Examples always make it easier. In other words, the more procedure is repeated, like flipping a coin for heads, the more likely the probability will approach 0.5. 50%. You got a 50-50 chance of getting a heads, right? That's what your gut says. But if you based probability on just a few flips, you might be cheating yourself out. So like if we flipped a coin 5 times, there's a chance we could get 5 heads in a row. So would we conclude that the probability of getting heads is 100%? No, of course not. You got to keep flipping, right? So if you flipped it more and more and more, like 500 times, then we should see that you're going to get a little bit of both, and it should start to even out to a 50-50. But again, so large sample sizes, keep going and going and going and going, and then it will approach that probability we expect. So small sample sizes we don't like. All right. Now, example 5 is just an example to avoid confusion. Like on the homework, you'll see a question like this, and it's very easy to overthink it, but don't overthink it. It says, express the indicated degree of likelihood as a probability value between 0 and 1. In one of New York State's instant lottery games, the chances of a win are stated as 4 in 21. So what do? Don't overthink it. All they want you to do is write this as a probability. So you just have to write 4 over 21 and then write it as a decimal. So 4 over 21 equals 0.1904, blah, 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 blah. So what would that round to? 0.190. All right. So not anything too drastic there. Again, just cleaning up some loose ends with probabilities. So we know about rounding. We know we can't trust probabilities based on small sample sizes. And we don't like using percentages unless it's requested. All right. So let's take a look at one more piece and then we'll pause this video. So we got complementary events. So the complement of event A, denoted by A with a bar over it, or A bar, whatever you want to call it, consists of all outcomes in which event A does not occur. So if the probability of event A happening is 0.995, what is the value of the probability of A complement? So that's everything else that could possibly happen. What do you think on that? Well, I mean, if you think of this as 99.5%, I know we said not to use percents, but sometimes percentages are an easier way to think of it. If the chances of this one event happening is 99.5%, what's the chance of everything else happening? It's got to get up to 100%, right? So the probability of A complement should be 1 minus 0.995, which is 0.005. So again, a very small chance of the complement happening if A has a really big chance of happening. But again, that's all the possible outcomes in there. So that's the key. So all the probabilities together, another way to think of it is that all the probabilities together have to total 100%. So all probabilities must total 100% or 1. So they have to add up to 1. And we're going to see that come back in the next chapter And we're going to use that in this chapter some more. So keep that in mind. All probabilities must total 100%. That's a pretty important one. All right, so we'll stop here, and then we're going to get into some significant results. So that's where it gets a little bit more interesting. So see you soon.